Now we're gonna talk about the complex Fourier integral and the Fourier transform. We know already that the Fourier integral can be represented as this. It's an integral from 0 to infinity, and then an integral from minus infinity to infinity of f of v multiplying cosine of wv times cosine of wx plus the sine of wv times the sine of wx. This is another way of writing the Fourier integral. However, using some trigonometric identities, we can also represent this Fourier integral as follows. That's integral from minus infinity to infinity, from minus infinity to infinity of f of v cosine of wx minus wv dv, and all this multiplied by dw. Notice that the limits of the integral are modified instead of 0 to infinity from minus infinity to infinity, because as these are all periodic functions, if we consider the integral from 0 to infinity, it will be the same as considering just the half of the integral that goes from minus infinity to infinity. So that's why we make that change there. And well, also we know that we can have another representation of this integral using something like this. Instead of having a cosine, a sine of wx minus wv dv. However, as this is a odd function, the integral from minus infinity to infinity of a same function will always give a value of 0. Just to take into consideration this, we can also now consider this other equivalency of the exponential of I multiplied by x is equal to cosine x plus I sine of x, and we will be using it by substituting it in the previous representations of the Fourier integral from minus infinity to infinity, again from minus infinity to infinity of f of v multiplied by e to the iw of x minus v dv dw, and this comes by adding these last two integrals here. So if we add these two integrals that we wrote before using this identity, we can then write the Fourier integral as as this, and this is what we know as the complex Fourier integral. Fourier integral, because of the I element there in the exponential. But also we can separate this exponential as a product of two exponential functions using something like this: 2 over the square root of 2 pi minus pi 2 pi, okay, 1 over 2 pi and its square root multiplied by the integral from minus pi 2 pi of f of b times e minus I w x dv, and all these multiplied by I w, sorry, this is not a x, this is a v and this would be an x dw. So this is another representation of the given complex Fourier integral, but here we can also make yet another consideration, that this will be minus pi to pi f of b times e minus I w x dx is considered the Fourier transform. So the Fourier transform of a given function f of b will be equal to this integral here. Hence, we can also write another representation of f of x equals to 1 over the square root of 2 pi from minus infinity to infinity multiplied by the Fourier transform of the given function f of w multiplied by e to the aiwx dw. And there we had yet another representation of the complex Fourier integral considering the Fourier transformation of the given function f.